Thank you very much, Stiliani, and thank you for inviting me to give this talk today. First of all, let me mention that this is joint work with Mark Rounsfield of the University of Lancaster and Peter Tolmie of the University of Siegen. So, explainable AI refers to techniques that enable the behavior of artificial intelligence tools to be understood by their users. And it contrasts with the black box that is typically the reality, I think, of many AI tools today. I just thought it worthwhile going through a brief history of AI. So in the first generation of AI, so-called expert systems mimicked human experts. So there was therefore an explicit decision-making model that could be inspected by the human experts to check if they thought the tool was providing credible responses to the data provided. And you can see examples of these rules over on the right. And then as AI moved to becoming more statistically based, techniques such as decision trees, which learn models from data, also enable an explicit model to be easily extracted. So here's a decision tree for, in this case, it's for prescribing a particular type of contact lens, or indeed not prescribing one. And you can see how the leaves of the tree provide the decision, and you can trace from the top to the bottom, following the evidence provided, to the conclusion that the tool, based on a decision tree, would reach. But things have become more complicated. Neural networks also learn models from data, and in simple neural networks, it is possible to, again, to extract some sort of decision-making model, which can be extracted and therefore inspected, although it is somewhat more difficult than with, say, decision trees. However, in the current generation of AI, multi-layer neural networks or deep learning, this becomes progressively more challenging to extract a model that users might be able to understand. And deep learning represents the current status of the art and is increasingly employed because it is delivering very powerful results. So the question is, how can we make the behavior of these deep learning models explainable? So there are some promising techniques for explainable AI, even for these deep learning models. And one example is contrastive explanations. In other words, what should be minimally and sufficiently present to justify the classification for some given data. And counterfactuals, that is to say, the minimal perturbation required to alter a prediction. And these can be applied globally to explain the behavior of the model as a whole, or locally to explain the behavior for a specific input. In this example you see here, which is designed to predict the class of a particular bird based on image features, an explanation model is used to predict candidate counterfactual evidence, or evidence that is discriminative for a counterclass. The two classes under consideration are that the bird is a scarlet tanager, or that it is a cardinal. And the system has predicted a cardinal, and the question is, why is it not predicting a scarlet to nature instead. So the evidence checker determines if counterfactual evidence is present and generates a sentence explaining the reasoning based on the counterfactual evidence that is not present. In this case, the counterfactual conclusion is not valid because the scarlet tanager has black wings, and the image clearly does not have that. And this example is taken from the paper by Hendricks et al., which you see over on the right. But as promising as these developments are, recent research acknowledges that our understanding of what constitutes explainable AI has focused too narrowly. So this is an extract from a recent paper by colleagues of mine, in fact, from the Turing Institute. And they say explanations are social, and as far as they involve an interaction between one or more explainers and explainees, interactive transfer of knowledge is required, in which information is tailored according to the recipient's beliefs and comprehensional capacities. We thus need to ensure explainable AI aims to develop methods for producing explanations that embody these characteristics. And they go on to say, there is thus a gap between explainability in practice and the goal of transparency, since explanations primarily serve internal stakeholders rather than external ones. That is to say, the state of the art of explanations primarily serves internal stakeholders rather than external ones. However, it does seem, looking at this quote and the work of others, that we are beginning to see a turn to the social in explainable AI. But what does this mean, and what are its implications for explainable AI research? So, to understand this, I argue we should start by unpacking the meaning of agency. So, sociologically, agency can be defined as a capacity of individuals to act independently. And one interpretation then is that agency is having mastery over technology. And this indeed is what explainable AI has focused on so far. Yet another interpretation of agency, however, is that it means being trusted by others to perform adequately whatever duties one is given to do. And this is particularly important when thinking about agency in the workplace, where people are involved in collaborative activities. And this is the interpretation that I argue has been overlooked so far in explainable AI research, and where the social character of explainable AI as a technology becomes more evident. So next, accounts. Staying with the narrow view of agency for the moment, that is having mastery over technology, being able to make decisions independently despite what a piece of technology such as an AI tool might propose. Having agency means AI tools must provide accounts of their behavior that can be assessed for their relevance in whatever activity they are being employed. And what's more, explainable AI must be capable of providing accounts that enable understanding in context whenever that decision that someone has to make has to be done. In fact, as soon as we bring context into it, we are already acknowledging that there may be social dimensions that have to be addressed. Might there be more than one user of an account, and might they have different skills and roles, for example? As noted by Mittelstadt et al., accounts may need to be tailored for different recipients. So turning now to accountability in the workplace, we begin with the acknowledgement that everyday life is socially organized, and for it to be that way, it must be possessed of accountable characteristics towards which we are continually oriented. We all routinely engage in making our actions observable, and so our behavior intelligible, and thus accountable to those who are around us. This natural accountability makes our behavior obvious to anyone using similar sense-making methods, and so affords trusts in our behavior, that our behavior is correct and appropriate in a particular context at a particular moment. And this is particularly important in the workplace. Participants are typically involved in collaborative activities in the workplace, and performing them in a timely and dependable way involves continually attending to being accountable to others. And here, natural accountability plays an important role, as we can see in the next example. So this is taken from work by Christian Heath and Paul Luff, one of many studies they've done looking at how coordination is achieved in workplaces. And it's a study of collaboration and control in the London Underground control rooms. And what it reveals is how the technologies available support a natural accountability in this particular setting. So you see there are a number of different participants: signal assistants, line controllers, and divisional information assistant. And they are particularly relevant to this explanation that I'm going to give briefly now of how accountability is performed in this setting. So to provide timely and relevant information to passengers, the divisional information assistant systematically monitors the service and the actions of his colleagues. For example, he overhears what the line controller is saying, the person who makes decisions about whether to divert services, interrupt them, whatever, in different circumstances. And he is aware of what the line controller is looking at, because they all have access to this large diagram, the fixed line diagram, which shows the state of the network in the area that they are responsible for. So overhearing and watching the glances of the line controller assists the divisional information assistant with making sense of what the line controller is doing and saying. And the layout of the setting and the design of the technologies in use affords this natural accountability. So what we can conclude from this is that accountability is a socio-material practice, and that technology shapes how workplace participants do being accountable through the ways in which it favors specific forms of accounts and accountability practices, whether it's observing where someone else is looking or overhearing what they're saying, and so forth. The design of explainable AI needs to be sensitive to this to avoid making being accountable more complex and time-consuming, which may happen when a new technology is introduced, and therefore the technological assemblies are changed. The practice must therefore react and respond to the new material affordances. And so to do this, we need to understand how being accountable is currently achieved in specific settings if we're going to deliver accountable AI into those settings. And in the next example, we'll see how being accountable is tied to being trusted. So this is from a study that myself and Mark Ransfield and others did some years ago now, but I believe it has relevance for what we're talking about today. It's from a study of the UK breast screening service. So let's remark in the first place that in the workplace, more formal methods of accountability are typically required. So this example comes from an ethnographic study of radiologists reading mammograms, as I said, in the UK breast screening program. And in this program, mammograms are read by 2 radiologists. And a recall or no recall decision, that is to say, to invite the patient back for further tests or not, is made on the basis of these 2 independent assessments. Typical features that are indicators of possible malignancy include microcalcification clusters, which are small deposits of calcium that are visible as tiny bright specks in the mammogram, ill-defined lesions, which are areas of radiographically dense tissue appearing as a bright patch that might indicate a developing tumor, so-called stellate or spiculated lesions, visible as a radiating structure with ill-defined borders, and also, for example, architectural distortion, which may be visible when tissue around the site of a developing tumor contracts. In other cases, it may only be asymmetry between left and right mammograms that is the only visible sign of some features. Here we can see a radiologist examining mammograms, and there are 2 views taken, called oblique and craniocordial, or CC. And these 2 views give the radiologist a number of affordances in terms of interpreting the image. And although mammograms may seem to be of limited value in terms of providing accounts of what is present, by, for example, comparing features across 2 views using a magnifying glass, or measuring features using their hands, the mammogram is turned into an accountable object, which furthers the interpretation of what the radiologist is seeing. Let's now turn to the screening form that's used to support this process, and is an example of a more formal form of accountability that is often required in the workplace. So the screening form is used to make an accountable record of the process. This process begins when mammograms are taken by the radiographer, who, as you see on the bottom left, adds information about the exposure, but also information that the radiographer is able to glean from the woman, such as cysts, moles, pain left breast and arm, GP thinks is muscular. So all this is recorded as an account of how the mammogram was actually taken. And similarly, if you look over on the right, the first radiologist doesn't just record recall or no recall, but adds further information, such as an annotation, which is, in this case, is new, indicating a feature that's not been seen before in previous mammograms from previous screening rounds. And the second radiologist adds a final annotation, BT, which stands for breast tissue, I think, HRT related. So these annotations are indexically tied to the mammograms through marking the simple schematics in the screening form. And they're provided as accounts of seeing what a competent and thus trustworthy radiographer and radiologist would be expected to see. And so not only is this a record, but this is also a way that the people providing or taking part in the process make themselves accountable for their performance in the process. And on the basis of that, they are providing evidence that they are performing in a trustworthy and acceptable way in terms of the quality and precision of what they're doing. So the combination of films and form provides accountability for everybody involved, and thus for the whole process. And as a formal account of the process, it may be revisited, of course, should there be any subsequent questions about the original diagnosis. So it happened that some little while later, we were invited to study trials for introducing a computer-aided mammography tool, which you can see here in this slide. This tool is called CADI. And at the top of the image, you can see there are the original mammograms. And at the bottom are two displays showing prompts for areas that the system thinks are suspicious. So the system performs an image analysis, looking for features that I mentioned earlier that might be indicative of possible cancerous changes. And if it finds them, then it produces prompts around particular areas that it thinks are suspicious. And this is what is displayed on the screens at the bottom of the image. And that's all it provides. So the radiologist has themselves to be able to provide an account for why a prompt should be ignored or indeed taken seriously, and offer an alternative account in its place if they decide that it's not relevant to any diagnostic purpose. As I said, the system is not capable itself of providing accounts of its behavior. And what we observed in this study is that radiologists try to come up with accounts, explanations based on accumulated past observations of the system's behavior. Although these are useful at times, they are nevertheless ad hoc explanations that may in some cases be unreliable and misleading. So here's some examples of explanations that radiologists came up with based on their exposure to the behavior of the system over a period of time. Reasons why they thought that, that the prompts could be ignored in particular cases. So in this case, the radiologist says, well, Katie's got a whole row of markers up here, but they're all on innocent things, nothing to worry about there. In other words, they're in areas that radiologists would not expect to find early signs of cancerous changes. So knowing the geography of cancerous changes, they could eliminate that prompt as being relevant to any diagnosis. And another example here, the radiologist says, I've seen this before. The computers mark something that I think is an artifact on that side. It's often along the edge of the film. So here again, they're noting the tendency for the system to produce false positives in certain regions of the image. So I think from this, we can conclude that systems that don't provide accounts for their behavior and do not provide explainability make for more work on the part of their users, may inhibit their decision making sometimes, because to ignore what the system says might count as evidence against them if they make what turns out to be the wrong decision. And so clearly some kind of accountability, some kind of explanation is what such systems require. So the question is, how can we understand how to provide these explanations, and also understand how these might be used in a setting where people have to demonstrate accountability to one another in order to perform in a way that supports the effectiveness of the whole team involved. So the method we used in those two studies is based on ethnography. And ethnography relies on participant observation and immersion in the setting. And since the 1990s, it's been used increasingly for gathering requirements for interactive IT systems. Its power lies in the production of so-called thick descriptions of work that can be mined for precise requirements and can be framed by a proper understanding of the activities to which they relate. And this has proved a very powerful tool for many kinds of applications, and particularly those that involve collaborative work, because what they provide is a way of understanding how collaboration is achieved in practice, and what the technological and social practices are, the social material practices are that enable that collaboration to work effectively and reliably. And myself and other colleagues, Mark and other people, have used ethnography extensively in studies of healthcare, manufacturing, policing, journalism, and so forth. So there's an agenda for taking explainable or research into explainable AI forward. I would like to see a number more case studies of AI tools or settings in which AI tools might be deployed in order to understand how currently accountability is achieved amongst participants in that setting, and thereby understand the affordances of accounts that will support those practices. So at the moment, subject to COVID, the COVID crisis ending, and which we all hope it will do fairly soon, we'll be doing some ethnographic studies of AI applied to the diagnosis of pathology lab slides under the Pathlate project. So on the left, you see the conventional existing technologies used to examine pathology lab slides, a microscope, and the slide is positioned, and the pathologist then uses the microscope to examine the slide in detail. What the Pathlate project aims to do is to develop computational AI tools which will enable the pinpointing of areas of a slide where there are possibly significant changes. And crudely, it might produce a prompt such as you see in the image on the right. So this study will endeavor to examine how to make these prompts explainable to the individual pathologist, but also then how that explanation might serve the process as a whole, and how it might manage the accountability that's required between the different participants in the whole process. Another case study, which I hope we'll be able to move forward with in due course, is healthcare. In fact, two such studies. One is the diagnosis of mental health conditions. There is an interest in using natural language processing to help clinical psychologists diagnose and track dementia by detecting language change in certain at-risk groups. The question here then is, how can these tools provide explanations for the changes that these tools are exposing? And then again, how do those explanations serve the work of the team as a whole in ensuring a reliable and dependable process? And the other healthcare example I want to highlight is what I'm calling the next generation of assisted living solutions. So from work I've done previously, I'm aware that current assisted living technologies involve the use of simple sensors such as fall detectors. And these are prone to error, false positives, which lead to carers, that is to say, family and friends of elderly people, to waste their time responding to a non-existent problem. And this can be challenging because quite often carers and whether they're family or friends or family or friends, they may live some distance away. So it's been argued that putting more sensors and gathering more data to be analysed by AI techniques will improve the precision of these assisted living tools. It will reduce the false positives and reduce the false negatives. So I think what's interesting about this potential case study is as follows: that the other case studies are all focusing on providing explanations to professionals, that is to say, experts in a professional way in a particular line of work. In the case of assisted living, or the next generation of assisted living solutions, introducing AI, I think calls for an understanding of how to provide explanations that work for lay people, which might reveal a much more varied set of requirements, perhaps, than might be the case for professionals, professional decision makers. The next case study that I would like to put to you is air traffic control. So this is an interesting environment or context for study, not least because it's one of the earliest studies where ethnography was used in order to reveal the collaborative features of work and how collaboration is achieved. And it marks, I think, what is referred to as a turn to the social in requirements gathering. And that's the reason I refer to turn to the social in AI, is because of sort of echoing that previous turn to the social. So a study of UK air traffic controllers was a key moment in the mainstreaming of ethnography in IT systems requirements gathering. And the Lancaster study revealed the key role of these paper flight strips, which have printed on them summaries of flight information. And what was observed is how controllers annotate the strips using a pen or pencil to record changes in the flight path, for example, who authorized those changes, etc. And this enables the controller to make themselves accountable for how they manage the flight, and thereby to help hand it over safely to the next controller. And you may have assumed, so here we see controllers annotating these different these flight strips, and you may have assumed that these strips, paper strips, have long ago been replaced by digital technologies. But in fact, this is not the case, as contemporary examples confirm, seen here. And what I think has been exposed here is how difficult it has been to replicate the affordances of paper as a technology for accountability practice using digital technologies. Finally, the national grid. So the National Grid Company manages the supply and demand over the UK electricity network. And you can see here a picture from the control room. It has various interesting features. It has the big display, which, as you might infer, shows the whole of the UK electricity grid. And then in the foreground, you've got controllers who are responsible for managing the supply and demand over different sections of that network. And not surprisingly, you can see that they're often engaged in conversation about the state of the network and what to do about it. Now, this is a possible setting for introducing AI tools for the following reasons. So traditionally, using traditional sources of supply for electricity, that is to say, coal, gas, and nuclear, the management of supply and demand is relatively easy because it's not too expensive to run up or to run down these supplies in order to maintain that match between supply and demand, which of course is necessary to maintain the stability of the network. Although controllers, of course, want to minimize the number of times they have to run up or run down these traditional sources of electricity, they are relatively easily managed. Now and in the future, of course, supply of electricity is increasingly moving towards renewables, wind, wave, and so forth. And these are inherently more difficult to manage. You cannot so easily run up or run down wind farms or wave energy electricity generators. And so you need more foresight about demand so that the renewables can be handled in a way that is consistent with maintaining that stability of supply. So this is where perhaps AI tools may come into play. So I think this is another interesting setting for looking at how explainability must satisfy the needs of individual controllers, but also provide accounts that can be shared between different controllers, people responsible for different parts of the overall management of the service, so that the overall dependability can be maintained. Now, it is acknowledged that ethnography can be time-consuming. Studies may typically last for weeks, and therefore there's been a desire to explore if it's possible to reuse findings from other studies. In other words, to generalize from site-specific studies so they can be employed in other settings. And what has emerged from this, again from the work of people at Lancaster, including Mark Bransfield, is the concept of design patterns. These have emerged as a promising approach to the problem of sensitizing designers to working practices. and not least is there value for providing reminders of what to consider when developing systems to support effective collaboration. So here's an example of a design pattern for collaboration, highlighting the role of an artifact as an audit trail, which I think is particularly relevant to thinking about explanations and accountability. It actually comes from the air traffic control example that you saw earlier. So it summarizes key features, cooperative arrangements in the site, the representations of activities, how activities are coordinated, and the community of use. And this may potentially, I think, as a way of structuring and identifying similarities between settings, provide a way of being able to accelerate what's learnt in ethnographic fieldwork to the application of developing explainable AI techniques that work across many different settings. So patterns are a way of conveying to designers some sense of the application domain and ways of allowing the results of workplace studies to be reused in new and different situations. And I'm looking to these to provide a way of, as I say, accelerating the use of what's learned from ethnographic studies for explainable AI. There's another example of a pattern, multiple representations of information and how that can be important for coordination, pointing to perhaps the need for multiple representations of explanations. So as I move to conclude this talk, I want to make a few comments about co-creating and co-evolving explainable AI. So I think this must involve a succession of steps, with iteration being an important part of the process. The first step must be to conduct a series of field studies and use those to begin the process of identifying design patterns for explainable AI. From this field work and from emerging design patterns comes the need to create prototypes, which can be evaluated with potential users in conditions that enable particular problems to be exposed and explored. And what's learned in these evaluation sessions can then lead to iteration of those prototypes and further evaluation until we get to a point where it seems that as much as can be learnt from that process as possible has been reached, and perhaps then the prototype is ready for being taken back into the real world. So that would be the final step, putting prototypes back into the setting. But it's important in doing that there is continuing effort to monitor and evaluate, because from what we know about introduction of new technologies, it's inevitable that additional requirements are going to emerge once the technologies are introduced into real settings, and people get to use them not in a controlled way or control setting, but in their actual work. And what's learnt in this process of using the technology will trigger likely further design iterations. And in the previous or other papers, we referred to this as design in use. So to conclude, taking explainable AI forward, bringing the social, putting the social into explainable AI, requires learning from ethnographic field work, identifying reusable design patterns for explainable AI, and following guidelines for co-creating and co-evolving explainable AI. Thank you.